What I do every time I'm out and I have my laser, I flash it at a star that's in the night sky, like a pulse, and then I turn it off. So if you leave the light on for 1 second,
Right.
there's a beam that's 186,000 miles long.
Right.
Okay. And so that is on its way to that star and maybe to a planet that'll see it.
So cool.
Yeah. So it's my space graffiti. I
go.
say Neil is here. This is StarTalk, Cosmic Queries, fan favorite Cosmic Queries. And this is the grab bag edition. Chuck, you ready for it?
Always loving a grab bag.
Yeah. The grab bags are fun because they're like random,
whatever.
They just dance around.
That's it.
And they keep me on my toes. I haven't seen these questions. So
they have the random beauty of a snowfall.
I don't know what that means at all. It means
you never know what you're going to get, but you know it's going to snow.
Okay. Is that your attempted poetry? Okay. You got a C+ on that one. All right. Give them to me, Chuck. Let's go right in.
This is Bjorn Furunap. He says, we seem to focus for obvious reasons on the what and the how of the universe. The why never seems to get much scientific attention because it assumes, I imagine, that there is a purpose which physics does not really need. With that in mind, is not the why an important factor for human curiosity? And should we not then seek to not necessarily find a reason for the universe, but encourage those who seek purpose and thus understanding? Okay.
Damn.
It's philosophical in nature.
Just at this time of the morning?
I know. He went... hey. So you don't need a why, is what I'm saying, but shouldn't we still ask why?
All right. So I have a response for that.
Okay.
I've thought deeply about this, by the way.
I know you have.
So in physics, we declare full understanding of something when we can account for all the behavior we've seen it exhibit and predict all future behavior that it might undergo.
Mm-hmm.
And we know what it'll do when we poke it, when we heat it, when we freeze it. Then we say, we understand this thing.
I know what you did last summer.
I know what you did last. I know what you will do. So let's take gravity for an example, okay? So you can say, well, what is gravity? How does gravity work? And then you say, well, why is gravity? You can, let's go in this sequence, I suppose. And I'm here to tell you that we can launch space probes from Earth, a moving target, and hit a moonlet around an asteroid, point blank, having sent a space probe to where it would be when they both got to the same point at the same time. Yes, it is rocket science. Yes, it is involved a precise understanding of gravity. We're good with that. If you want to try to now understand why, why did the spacecraft hit its target? Because we did the calculations and we gave it the right acceleration and we knew where the target was when it was going to get there. That's why it hit.
I love that joke, by the way.
Which one?
Why did the... Never mind. I'm sorry.
Why the asteroid cross the road?
Well, because the way you said it was like, why did the chicken cross the road? And then your answer was, because we did the calculations and we saw exactly where it was going to hit. Like,
my favorite answer to why did the chicken cross the road is, can't the chicken cross the road without having its motives questioned every time?
Okay, let me give you the black version of that.
Oh,
Why did the chicken cross the road? Why are you in my business?
Who asked you?
Exactly. All right.
Why? That's why.
That's why.
All right. So the point is, you can say, let's say the pie is up on a table and it falls to the ground.
Right.
You say, why did the pie fall to the ground? And I can say, well, because you pushed it.
Right.
That should be sufficient response to that why question. Okay? Well, you pushed it, but there's a little more going on. If we were floating in space and you pushed it, it wouldn't fall at all because there's no net gravity vector there that will have the thing fall. It'll just, it's in free fall. It'll just float.
Okay.
So there are plenty of questions where the why is a completely satisfactory answer. We can give you a why for it. Okay. Why were you T-boned at the intersection? Because you ran the light. Okay. There's no end of questions for which the why, there's no end of situations for which the why question has a completely legitimate answer that we're all satisfied with.
Right.
Okay.
Yes.
It becomes an issue if you try to take a philosophical step and then try to explore why as the consequence of intent.
Gotcha.
In so doing, you are handing intent to things that might have no intent at all. And therefore, you are forcing an intent where there might not have otherwise been one. And therefore, you're forcing an answer. And now you're chasing ghosts at that point.
Right. And he answered his question, and you just confirmed it. He said, it's not necessary. So basically what you're saying is, for the purposes of science, if what we're really concerned about is science, we don't need that.
Well, or I have answers that are science that are satisfactory answers to the question why.
I don't, and I should have said that too. I don't need to go beyond that because the science has been satisfied. So beyond that,
or you're satisfied because I have a scientific answer for why something happened.
Right.
Okay. Because, why is Earth warming? Because we are adding greenhouse gases to the chemical mixture of the atmosphere.
Right.
That is a complete contained answer to the question why. So I will not cede the accusation that science is not about why. I will not say that.
Right.
There are plenty of why questions where we are all completely content with the scientific answer for it.
Right. And so there you go. And like you said, going beyond that, you're creating a dragon and then chasing the dragon.
You created the dragon, correct.
You created the dragon and now you're chasing the dragon.
And you want to give meaning and significance to the existence of the dragon you created, where there was never a dragon there to begin with.
There you go. Well, look at that, Bjorn. You started off by saying that you were going to ask a profound question. I got to give it to you.
But what I do want to say is,
go ahead.
If you're going to say, well, because one of them is, what is the meaning of life? That's not a why question. That's a what. Okay. And I might say the meaning is what you make of it, given that you have power over objects and events and things and places and people in your influence. You can create meaning rather than just simply look for it. Most people are looking for meaning like it's under a rock or behind a tree. Right. And then they spend their whole lives in search of meaning. And I'm saying, make the meaning. And derive your meaning from that.
Okay.
Now you might say, well, why should we have meaning in life? I would say, in our experience, people with more meaning in their life lead a more fulfilled life. And to be fulfilled is, in our short time on Earth, maybe something we should all seek. So you can have a better time. Why do you want a better time? You could keep doing this.
Yes.
But I would ask you, what is the end game of that? Where will you be satisfied with your sequence of asking why? Because if you're never satisfied, then you're not useful on the moving frontier of science where we can land a target moving in space.
Right.
Where we can take pictures of the early universe in a telescope parked 1 million miles in orbit around Earth, 1 million miles from Earth, called the James Webb Space Telescope. While you're asking questions, we are answering questions. While you're asking why questions in the dragon that you just created, we are answering questions and advancing civilization. So, yes, I am discounting many people who are asking why about many things. But so many other things where you ask a why, the answer when drawn from science or even from culture or ever else is a perfectly satisfactory answer. that no one would further question.
Well, there you have it. That was very, very necessary.
Yeah.
All
yeah.
of that you just said, very, very necessary. I mean, it speaks to so many other things than just this question from Bjorn. There's so many
Yeah, it
other
does.
things.
It stretches
Yeah.
beyond the limits of the question itself. Yes.
Wonderful. Wow, good stuff.
Keep it coming.
Here we go. Let's go to our next one, which is Jay Salmon. Or is it Salmon? I don't know.
I don't know anybody who pronounces the L in salmon.
Neither do I.
Yeah.
It's ridiculous. It's salmon.
Well,
Anyway,
the salmon rusty.
you're right. That
S-A-L-M-A-N,
is
salmon.
rusty.
Yeah. Mhm.
Okay, so he says, when matter is consumed by the black hole, does it retain its form as protons, neutrons, etc., or is it compressed and ripped apart to the more basic elements of the particles, like quarks, etc.?
I can answer that very clearly. We don't know.
Ooh.
Next question.
There you go. Let's move on.
No. So, matter and all the identity it carries as it goes down to the singularity. It's the singularity where we're idiots. That's unfair. It's a singularity where we have profound ignorance. All right.
Right.
And Einstein's theory of relativity, which gives us the black hole in the first place, does not take us to the singularity. It's a limit to the theory of relativity. That's why we have string theorists who are picking up the slack there. We do not know what happens to matter at the singularity. We just don't. We do know that the black hole remembers what it ate, because Hawking radiation, where particles come into existence from the energy of its gravitational field just outside the event horizon, that gravitational energy through E = mc squared spontaneously becomes a pair of particles. One side of that particle falls back in, the other side escapes. If you get the inventory of the particles created out of the gravitational energy field, that inventory of particles exactly equals the history of what the black hole ate. Remarkably, somehow the imprint of what it ate is remembered in the gravitational field of the black hole itself.
Damn.
Yes.
That's pretty
profound.
Wild.
It's profound.
Just wild.
Because you didn't reach back in and pull it out.
No.
It
appeared.
It appeared out of the energy outside the event horizon.
Look at that.
It's like, oh my gosh. And of course, Stephen Hawking was at the centerpiece of that.
That's amazing. Yes. Hawking radiation, the
Stephen
evaporation
Hawking,
of a black hole.
Rest in peace. We actually had him on StarTalk back when we were on the National Geographic channel.
Yeah.
And you might be able to dig it out in I guess Disney Plus has the entire Nat Geo catalog. But yeah. Mm-hmm.
It's good stuff, man.
Yeah.
That is good stuff. All right, here we go. Colby Lapresi from South Carolina.
All right.
And Colby says, once again with the black holes, if a black hole was smaller than my body, beyond the event horizon in all directions, would it still rip me apart atom by atom?
Yes. Don't ever, no, just stay away. Because what matters is not the size of the black hole, how much mass. So if Earth were a black hole, it would be the size of a plum.
Right.
So now take all the mass of the Earth, cram it into a plum, and you want to walk by it and believe you're going to stay intact? That is not going to happen. It will suck you in and it will funnel you down and you'll be spaghettified, funneled, and that's it. And just kiss your ass goodbye.
Look at that, Colby.
Because you wonder how something your size can fit into something that small. The very fabric of space-time narrows towards the black hole. So you will be funneled, basically extruded through the fabric of space and time, like toothpaste through a tube.
That's crazy, man, when you think about it. It's so hard to just like really
to fathom it. Yeah, to have a black hole that fits in your palm of your hand, and then it sucks you down into a tiny point.
I mean, it's really, it's oddly terrifying and beautiful at the same time.
Yes, yes, yes.
Wow. Okay.
All right. Yeah,
All
you're
right,
not
here we
getting out of
go.
that one.
We're,
Just keep
we're,
your
we're
distance.
banging them out.
All right.
Here. Alan Rayer says, can someone address the comet C2022E3? Hey, Neil, just want to let you know I'm a big fan, and I'm coming to you from the Isle of Malta.
Oh my gosh, cool. Well, when we come back from our first break, we will address that question on StarTalk. We're back. StarTalk Cosmic Queries, Grab Bag Edition. Chuck, we left off with someone asking me about Comet. What number did they?
Our good man Alan Rayer from the island of Malta in the Mediterranean wants to know, hey, what's the deal with C2022E3?
Well, he gave me the phone number of the comet. Cool.
Yeah.
Cool. So that's been called the Great Green Comet of 2023.
Right.
By the way, that ID is includes the year it was discovered, 2022, and the semi-month it was discovered. So there's that ID is packed with information for someone in the know to know when it was discovered. Wow. And so B, this comet, based on its orbit, it comes from what's called the Oort cloud. This is a spherical shell of comets that surrounds the solar system, but it extends halfway to the nearest stars. And comets that come from this can come in from any direction at all.
Yeah.
They can loop in from above, from below, and their orbits last tens of thousands of years. There is no comet that we see from the Oort cloud that was ever seen in the history of civilization.
Wow.
So you might say to yourself, well, I better go out and watch it. Well, every Oort cloud comet is that. So it's possible for something to be rare but uninteresting.
Okay.
Because they're common, right? Right. Just keep that in mind. So with this comet, it's made the news primarily because there's a chance people could see it.
Okay.
And right now, like last night, it would be among the days of peak visibility. I looked up, I didn't see it. I'd have to find it with binoculars. So it's got a lot of press attention. By the way, we discover hundreds of comets a year.
Right.
So a comet alone is not some, don't invest special attention to the fact that a comet was discovered. They're as common as blades of grass on a lawn. There's trillions of them that orbit the sun. So A. B. The many comets are very faint, and you might catch it with binoculars, and you can see the green in a telescope because it's a green comet. Remember, our retina has rods and cones.
Yep.
And the rods are sensitive to shades of gray. The cones are sensitive to color, but they require higher intensity light in order to get triggered. So if you dim the lights in a room, if you look at a room in the dark, but just light leaking in from a street light, something through the window, that room is not vibrantly colored.
No.
It's basically shades of gray.
Gray. Mm-hmm.
Okay? Mm-hmm. Because your cones, your rods are taking care of business there, just so you can see your way anywhere. Only when it gets brighter did you start registering the colors. So dim comets, no matter what color they are in a telescope, typically you don't notice that with your eyes, unless you can see them through a big telescope, okay, that can make the object bright enough to trigger your cones. So where to get the green from? The green, well, we did an explainer on the comet. I think we did. Yeah, we did an explainer. So cyanogen is one of the molecules that when it interacts with sunlight, gets warmed, radiates light. There are different ways a comet is rendered visible, and different chemicals will have different color signatures, and that's part of what tells us what comets are made of, right? I mean, it's a beautiful, wonderful thing. So I love me some comets, but most of them are just not, they're not something you're going to write home about and say,
boring.
Were you alive in the 20s? Yeah. I promise in your lifetime we'll have a really good comet, because every 10 or 20 years or so, a really good one comes around. Then I wouldn't count this among them.
Now, the real deal is the action is where the asteroids are, my friend. Don't worry about the comets. The action is with the asteroids. That's okay.
Yeah, but asteroids are dark and they only reflect light.
Right.
And even if they do reflect, they're dark, so they don't reflect much light. So they can come up on you and you wouldn't know it. Whereas comets, they, here I am.
Yes, exactly.
Look at my tail. Look at
Comets
my
are
beautiful.
like, yeah. Look at me. Look at me. Asteroids are just like, yo, I said, give me your wallet.
That's right.
Hey, man, where'd you come from?
No, you said that way too glibly. Give me your wallet. No, the more likely the asteroid's gonna say, yo, give me all your species.
Yeah, tell me about it.
Ain't even about the wallet at that point.
Yeah. I'm trying to figure out if there's ever an asteroid big enough that would blow off the entire atmosphere, because anything that hits the atmosphere becomes like the ocean or anything else. It would have to be penetrated. So suppose you had something big enough that it hits the atmosphere, but it's so powerful that it blows the atmosphere off. But would it then be so big it would destroy the planet?
Next question. No. Right. Here's the thing.
Yo, that
the way
that
you
was
want to
cold,
get rid of,
man. That was cold.
I know it was cold. You want to get rid of the atmosphere. You get enough asteroids hitting Earth to heat the atmosphere, and the hotter atmosphere expands, and we might lose some outer layers because you have the molecules start moving faster, and some will achieve escape velocity,
right?
And so, but a large enough asteroid just punches a hole in the atmosphere. The real damage is because it doesn't leave its energy in the atmosphere.
Gotcha.
The energy, it'll barely be slowed down by the atmosphere.
Gotcha.
And then it hits Earth's surface, and that's where it stops moving. Hey, where did all the kinetic energy go? It made a crater. It burned the forests.
Right.
It
became a shock wave.
Shock waves. That's so you have to ask where look at the energy budget. Where did it go? That's where the damage will occur.
Okay, cool, man. That was cool. All right, here we go. This is Nick Davis. He says, hello, Dr. Tyson and Lord Nice. This is Nick from Australia. I was wanting to know more about how gravity and its influence on time were to influence light. On the hypothetical Miller's planet and Interstellar, what would happen if someone orbiting outside of the time distortion were to point a super powerful laser pointer at the planet? Would the beam be dimmer? Or would the night sky look like what would the night sky look like for someone on the ground compared to someone in space?
Ooh.
And let's take out atmosphere so that we don't have those distortions.
Right. So no, we good here. So here's what's interesting to do with your laser the next time you're trapped in a black hole. You can try to point your laser out of the black hole and see if anybody gets the signal. They won't. All right. Why not? Because it's climbing out of the gravitational well that the black hole is. And for every little bit it ascends, it's losing energy. So the energy profile of your laser will become lower and lower and lower energy until there's no energy left at all and the light does not escape. Wow. If you were just outside the event horizon and did the same thing, the light would escape, but it would also be shifted in energy. And it's called a gravitational redshift.
Look at that.
Gravity redshifts the light. And so that's what would happen to the light. This was only about light, or did they also ask about time?
Well, yeah, so he started off saying, I wanted to know about gravity and its influence on time.
Yeah.
And light.
And if he remembers from Interstellar, they're on a planet orbiting a black hole.
Right.
And they are severely time dilated.
Yeah.
So that minutes to them are years to the folks orbiting far out. That's right.
That's the scene where he comes back and the guy is old, right?
He's old, correct.
Yeah. Wow.
Correct. And it was subtle, but they got it in there. At the end, the what was it? They showed someone in a hospital bed, or was it? I forgot.
Yeah, I think that was his daughter.
That's who was older.
Who was older than he is.
Correct. Because his because his life was prolonged for having been in a very intense gravitational field.
Right.
So yeah, all these are real and you can calculate it. And by the way, we do this every day with GPS satellites.
Mm-hmm.
GPS satellites are in a different gravitational field compared with us. Yes, it's still Earth, but we are closer to Earth's center than the GPS satellites are. So just the way they did in the movie Interstellar, except it doesn't have to be a black hole to mess with your time. It just will mess with it at a different level, at a lesser amount. So our time on Earth is ticking more slowly than the time in GPS satellites.
Right.
Yet the GPS satellite is handing us our time.
Right. Wow.
So how is it that they match up? We have
I know how.
How they do?
Because the GPS, they're on CP time. See, a lot of y'all don't know about CP time.
Okay. All right. Thank you, Chuck.
But see, GPS, y'all don't know.
Mm,
They down with CP time, and they cool with it.
They're cool.
And I'm not going to explain what that is.
Okay, Google CP time.
If you know what it is, you know what it is.
Google CP time. All right. So, Chuck, I don't know what Chuck is still in race therapy.
Hey,
Chuck
listen.
is still in.
Come on. That's amazing.
This stuff. All right. So the GPS satellites are no, you're saying that on Earth we'd be CP time because the GPS satellites being in a different low
that's right. We're closer
field.
to the gravity, so we are slow.
We're slow. And
Right.
the GPS satellite is ahead by a calculatable amount.
Right.
And so when it gives us our time signals, it pre-corrects it using the equations of Einstein's general theory of relativity so that we get the proper time on Earth's surface.
That's just, I'm telling you, it's just fantastic.
Yeah. And then people say, well, I don't believe in science. I don't want to do science. It's like, do you know what we do?
Exactly.
For a living?
Exactly.
Don't get me started here, Chuck.
You can't even tell time. You're talking about you don't believe it. You can't even tell time.
I don't decide. What do scientists know?
Science do? Yeah, I'll tell you what they put crap in the sky that calculates the time that you can't even tell. That's what science does. And you got the nerve to sit around like, because seriously, do they really know? Do they really? I'm not sure if they really know. Okay. That is just so, I just love that it's so elegant in the fact that it's, establishing the time, but then relaying the time after it equates what the time will actually be for you. That's freaking amazing!
It's for you because it is touched by Einstein's general theory of relativity.
Damn!
Yes.
Oh, that's just so good! All right, okay. That's so freaking cool, man.
Like, what do people think scientists do, right? Do you think we're just sitting around?
So cool. Oh, man. All right.
Right, next one.
Here we go. This is Kyle Marston. And Kyle says, I know how I perceive the universe. And I know you and Neil, you perceive the universe as well. And that our perceptions are pretty similar as biological entities from Earth. What insights do you have, Neil, as we now have artificial intelligence? How will they perceive the universe around them? Like, are they going to go straight to Dan Simmons' Technocore or more like Tchaikovsky's Hive Assembly? Wow.
Okay.
Holy crap.
Okay.
I'm going to tell you the truth, Kyle. I'm sorry I read your question. No, I'm joking. That's pretty wild.
Yeah, okay, so I have several ways to address that. One of them is, I don't know that people thought much about AI's sensory system.
Ooh, very nice.
Right? So can AI feel pain?
I love it.
And can AI taste?
Mm-hmm.
Right?
Right.
But we know we can outfit it with capacity to hear and to see that is vastly greater than our own.
Yeah.
All right. And self-driving cars will be able to see at night.
Those are senses.
These are senses, correct.
Right.
So we can outfit AI with sense. I don't know that we can quite have them taste things. We'd have to.
Why not? Why not? Think about this.
No,
Your olfactory sensors in your brain basically are responding to a molecular stimuli.
yes.
So
Completely.
why wouldn't we be able to program what that molecular makeup is and then give the computer the same
Yes, we can.
response?
However, yes, we can. However, we just have centuries of efforts to improve our capacity of sight with microscopes and telescopes, and to improve our capacity to hear with sensory devices and microphones. So we don't. We're much more behind in having machines that can taste. Let's put it that way.
Okay, I got you.
Okay, so we can have a machine that can analyze the chemicals of what's touching. There's mass spectrometers that can analyze chemicals. We can say, if it's this much that tastes salty, this tastes sweet, and this is the umami. We could teach it that, I guess. Sure. But then it has to sort of bite into you, right? To taste it, right? It needs some mechanism to taste.
All right. Right.
It can't just be a box on the table.
It'd be the difference between someone telling you what something tastes like,
correct,
and you putting it in your mouth,
correct,
and tasting it, right,
correct,
right,
all right. And so because you can hand them all the ingredients that went into your pie, and then they can analyze those ingredients, and they say, good, I want some ice cream with that in a pie a la mode. They might do that, but would they want to? Right. Does AI have our urges? Does AI have our, typically it's only thought of in terms of problem solving and this sort of thing, not in terms of receiving the sensory pleasures of what it is to be alive. But let me add to that in science, there are people who run around and say, I have a sixth sense. And they want you to be impressed with that. And I say, well, I'm a scientist and I have a dozen senses.
Wow.
Because I have sensors that can detect all manner of things happening around me that my 5 biological senses can't. I can detect polarization. I have a gravimeters that can detect slight differences in where the mass is beneath our feet. I can have devices that can detect radioactivity that we cannot sensorily do. I can detect wavelengths of light that fall outside of the visible spectrum. Yeah. All right. So I have dozens of senses. You're not impressing me with your sixth sense.
Wow. Yeah. So why don't you take that little parlor trick back to your seance? Okay. I'm sensing someone who's passed with the letter J. Wow. So okay, so that's cool. So
I sense someone here with a relative that has an X in their name.
You're right.
Those seers don't last very long on the block.
That's so funny. Yeah, they never do that. That's right.
Well,
there you have it, man. There you go. So let me ask you this as a follow-up to Kyle's question. Do you think it's a good idea to, and not as a means of anthropomorphizing machines, but do you think there's any true benefit in giving them our sense of taste and smell,
whatever I want,
emotion, and
whatever it is? I want them to think that humans taste badly.
It's people. It's people.
I don't want them thinking that we have tasty snacks. That will not go over well.
Oh my God, that's so great. Right. That's very funny. All right, here we go. This is Christopher Fowler, and he says,
"To serve man." Yeah, that's right.
Yes, exactly. Christopher Fowler says, "Hey, Neil, what's up, Lord Nice? First, I am just a huge fan of yours, Neil. Thank you for providing the spark of curiosity to us commoners. Second, thinking about the Stargate franchise, could there be a discovery in nuclear fusion advancements and understanding, and I use this term very loosely, of the quantum, being able to establish an Einstein-Rosen bridge for interplanetary and interstellar travel?" Wow.
So let me first agree that we kind of need that if we're going to go between the planets.
Right.
and no, not the planet, between the stars and
Stars.
galaxies. Yeah, planets takes, a dozen years. That's within a human lifetime. But to the nearest stars, it's tens of thousands of years. We need a wormhole. Stargate is basically a wormhole. They didn't call it that, but that's what it was. And except there was just this metallic ring that, it's mixed with mysticism and magic and this sort of thing. So you step into the ring like time tunnel. Those who remember this from the late 1960s, you step into the ring and you're transported through time. Do you know where they went in the very first episode of Time Tunnel?
I do not.
They went to the Titanic.
Why?
And the guy's on the ship he's on the deck of a ship, and he's, oh, I'm on a ship. Good, because they got lost in time, right? So he's on a ship, and I wonder where it's at. And he walks by, and the camera moves with him, and then the camera moves back, and you see the buoy that says Titanic.
That's great.
And you say, oh, and because there was not a second voyage of the Titanic, right? So my boy's going down on this trip.
That's great.
And apparently they took a poll about if you could move through time, what historical event would you want to witness? And many people said they wanted to see the sinking of the Titanic. So it has been hypothesized that that's why the Titanic sank. Because when the time machine was finally invented, everyone went back to the Titanic, and there were too many people for the lifeboats.
Oh, that's funny.
Because they were all time travelers and they all died.
And you know what? If they wanted to go back in time to the Titanic, they deserve to die.
No,
That's all I'm going to say.
that ain't right.
All the places you can go. You're like, I want to go back and see a bunch of people drown. Listen, I don't care how much you don't like rich people. It's a little too macabre to want to go back to the Titanic. You got what you deserve. You right on there with them when it goes down. Okay? I hope Leonardo DiCaprio grabbed you by the head and pulled you right down with him, just like, sorry, Grace. Okay. Yeah.
Are you done, Chuck?
I'm sorry. I don't know where that came from.
All right, so where was I talking? So it was just about the Stargate, the possible Stargate portal. We know how to make we know what is required to make a wormhole.
Right.
We just don't have this material. So it needs something, it needs the equivalent of negative gravity, negative energy substance. And we don't know what that is or how to make it. But if we had it, we can make a wormhole.
We can do it. There you go. Great question, Chris.
All right. We got to take a break, Chuck. And when we come back, the third and final segment of StarTalk Cosmic Queries, Grab Bag Edition on StarTalk. We're back. StarTalk Cosmic Queries, Grab Bag. We left off that last segment. We were talking about Stargate. Chuck, do you know I have a cameo in Stargate Atlantis?
I did not know that. Now,
do.
That was the TV show?
Yeah, TV show.
Oh, man, I love it.
Yeah.
What happened? Please tell me. And now I gotta,
I'm an old friend of one of the characters, and I can't act, so it's embarrassing. So I shouldn't have told you.
Oh,
so
no.
Never mind.
Okay, let me tell you why it's not embarrassing.
Why?
Guess how many appearances I have on Stargate?
That's
so
Stargate.
To hell with the haters. See, that's what I say to haters. To hell with you.
Because it's a cameo, people give you a little more slack for your inability to act.
It's so cool.
Yeah.
I mean, shoot. Please, I can't act either, and I've been in a bunch of stuff. And I'm supposed to be an actor.
Hired as such.
Right, they hired me for it. I still can't act. So guess what?
All right.
You should be very proud. Don't ever shoot, please.
So next one.
All right, here we go. This is Jason Whitehair, who says, greetings, Dr. Tyson, Lord Nice. With the expansion of the universe, likely never ending, and space-time with it, will individual galaxies be ripped apart by the expansion as objects get further apart from each other? Will individual bodies be then ripped apart and so forth? Ooh.
Yes.
What?
Ultimately, as galaxies spread apart, this pressure within the vacuum of space, we call it dark energy. We don't know what it is, but it's there, and it's doing its thing. And it is most of what is driving the universe right now. That dark energy will ultimately overcome the gravitational attraction of stars that are held together within galaxies.
Right.
So it'll start ripping apart galaxies. Then it'll rip apart star systems as it pulls planets away from their host stars.
Wow.
Then it will rip apart solid objects as the molecular bonds that hold the atoms together are broken. Then it will rip apart atoms where the electrons are ripped from their nuclei. Then it will rip apart nuclei. Then it'll rip apart the fabric of space and time on the Planck scale. And at that point, it's the end. That is called the Big Rip. And that will take place in 22 billion years unless something stops it.
Sleep well, Timmy.
Have a nice day.
Jeez. God, that's awful.
It starts ripping apart protons themselves. Right.
Wow.
This is serious stuff.
Look at that.
And by the way, when that begins to happen, it happens rapidly. So it's once starts things getting flying apart, it's because the more vacuum there is in the universe, the more is this pressure to accelerate it.
Gotcha.
Right. So it's a runaway process.
So okay, gotcha. Yeah, right. It's like a snowball rolling downhill.
A snowball.
It just keeps
Correct.
going boom, 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 bigger, 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 bigger.
Bigger. And the bigger it is, the bigger it gets.
Look
right.
at that. That is insane.
And it's called the Big Rip. By the way, in our second StarTalk book, guess what it was titled, Chuck?
No, go ahead.
Cosmic Queries. In our second StarTalk book, one of the questions is, what is the future of the universe? And we show all the scenarios and one of them is the Big Rip. If you get that book, you'll have way more conversation about it than anything I just laid down to this recording.
Fantastic.
Your Cosmic Queries.
Cosmic Queries.
You got it.
All right. So this is Bruce Ryan. Hey, what's up, gents? Bruce from Virginia here. I'm wondering what happens to all the heat and energy emitted from stars. Is it actually heating up the universe? Or does it just travel until it hits something and then that something absorbs that heat? And then what happens when that heat
I
is
love
absorbed?
it. Okay, so both of those happen. So what happened is the heat generated from a star goes out in the form of photons of light.
Right.
Okay. And that will travel until it hits something else and then it gets absorbed. So you'd think it would just be this tennis match going on back and forth. However, in the expanding universe, the energy of the photon is diluted into the space that has been expanded for it. So the energy, the total energy is still there, but it's diluted. So in other words, if you have a box of energy, right? Now I take that energy and spread it into a box twice that size.
Right.
It's the same amount of energy, but the energy intensity is now half in each place. Now make the box 1,000 times as large.
Right.
That energy is all spread out. The energy intensity is dropped by a factor of 1,000. Add it all up, you'll recover all the energy you began with, but the energy density is thinner. And as the universe expands, the energy density drops, and so the temperature of the universe drops. And right now we're 3 degrees Kelvin, 3 degrees absolute on the scale, and it's dropping.
Look at that. Wow. That's
by the way, the James Webb Space Telescope, part of why we put it where it is that it's far away from Earth. So it's 1 million miles from Earth, and it only ever points away from the sun. And it has these baffles that will absorb sunlight that hits it, but re-radiate it back to the sun. A little bit moves through, and we have another baffle that will absorb it and re-radiate back to the sun. And so we have 4 or 5 of these layers. And each layer, less and less of the sun's heat energy makes it through to shield the telescope from any infrared energy that could hit it from the sun. By shielding away the sun, it drops into equilibrium with deep space.
James Webb Coppertone.
Yeah, I guess you can consider. I guess it is like sunscreen. It's
right?
sunscreen. It's a cosmic sunscreen. Thank you, Chuck, for that analogy.
Yeah.
And by doing so, the sun, which is relatively close to it, all things considered, will not then heat it up. And so any heat that's in it will just radiate back out into space. So This is the thermodynamics of technology and engineering and in the universe itself.
Wow.
Yeah.
That is cool.
Yeah.
All right. Man, we're getting through a lot today.
Yeah, look, keep it coming.
I can't believe it.
Keep
All
it coming.
This is Cameron Bishop. He says, hey, Neil. Hey, Chuck. I like to think that if I waved at the night sky, someone out there in the distant past is waving back. Now, in the last century, we have gone from stars might have planets to stars on average have lots of planets. If you run the numbers, the amount of planets out there is huge. Given that we exist, it's not fair to say that with life here on Earth in one hand and the amount of planets in the universe on the other hand, that life is statistically likely in the universe? And what sort of implications does that have? Either scientifically or philosophically.
The day we discover life in the universe, it will signal a change in the human condition that we cannot foresee or imagine. Yes, it is highly likely that life is thriving elsewhere in the universe, not out of wishful thinking, but we're made of the most common ingredients in the universe. So whatever life was doing on Earth, it was highly opportunistic, A. B, life got going almost as fast as it possibly could have. Within 100 million years, this sounds like long, but it's short on the timescale of Earth. Within 100 million years, we went from organic molecules, which are plentiful in the universe, to self-replicating life. And the universe is old. So you combine how much time we've had, how quickly Earth managed to create life, how resourceful life is, and to assert that we're alone in the universe can only be done based on some philosophy that has no foundation in science.
Wow.
Yeah, it is.
That's it, man.
That's it. That's it. And so if you wave, surely someone is waving back. I have no doubt.
Back.
Yeah.
That's it. And
your wave is not going to get to them
right
for, 100 or 1,000 light, years traveling at the speed of light. What I do every time I'm out and I have my laser, I flash it at a star that's in the night sky, like a pulse, and then I turn it off. So if you leave the light on for 1 second,
right,
there's a beam that's 186,000 miles long.
Right.
Okay. And so that is on its way to that star and maybe to a planet that'll see it.
So cool.
Yeah. So it's my space graffiti. I'd say Neil is here.
And so when they show up,
so I want to get picked up. I want to meet the aliens.
When they show up and they're just like, we saw your green signal, and you Neil.
No, they'd say, well, who the hell's been waking us up in the middle of the night?
Exactly. We saw the signal. And, oh, that was our man Neil. Yes, and by the way, you are now all serving our god Flarm. What? Yeah.
Chuck desperately wants to write a screenplay. That's clear. Right.
Yeah. It'd be kind of cool though if like they landed and they were on their version of what we had as the Crusades.
Yeah.
Except that they do it on an intergalactic basis.
Yeah, okay.
You know?
Mm-hmm.
Yes. Anyway. All right. Tyler J says, hello, Dr. Tyson. Hi, Chuck.
Where did they say where they're from? I always want to know where they're from.
What options are there to resolve the crisis in cosmology? I heard that new data from James Webb Space Telescope has further separated the two values we have for the Hubble constant.
Yeah. Yeah, this crisis is, by the way, when I was coming of age, I mean, astrophysically, we didn't know the size of the universe to within a factor of 2. The size or the age of the universe.
Right.
To within a factor of 2.
Right.
To show you how precise modern cosmology has become, we are now arguing over a 10% difference between two numbers. And the reason why it's called a crisis is each of those two numbers is precisely known, so that the error bars, the uncertainties do not overlap.
Right.
So even though they're close to each other, especially compared to when I was in school, they don't overlap. And so it's called a crisis in cosmology. And crisis, I think, overstates it. It's an unsolved problem. Right. Every unsolved problem is not a crisis. It's just an unsolved problem.
Right.
And somebody's wrong. Okay? Period.
That's it. So, and there's the answer. Somebody is wrong.
No, or you're measuring two different things and you think it's the same thing.
Exactly.
Okay, yeah, you can measure the tail of an elephant to the blind man and the feet and the tusks and the trunk, and you could tell each other that the other person is wrong, but maybe you're measuring the same thing, but in different parts, in different ways, and collectively you all are describing one object, and it's the elephant.
Exactly.
You're both describing the universe, but maybe you came at it from different sides of the elephant.
Look at that.
So I'm not worried about it. It makes good headlines. That's all.
Yeah.
I'm not worried about it. Yes,
Wow.
James Webb will help us address this. Yes.
That's fantastic. That's wonderful.
By the way, I think in Cosmic Queries, we do talk about the crisis. The cosmic, I think it's in there, in the future of the
crisis
universe.
Of cosmology.
Right. It's called tension. It's called cosmic tension between these two different measurements. So again, in Cosmic Queries, I hate to sound like a ad for the book, but yeah, I mean, it is an ad for the book. We put a lot of effort into that book. Yeah.
The crisis in cosmology, not to be confused with the crisis in cosmetology. Okay. Which is, how dare you put that eyeshadow with that lip color?
No, you know what the crisis in cosmetology is? I wrote about this in Starry Messenger.
Okay.
It's an alien comes to visit, and they see that people with straight hair curl it, people with curly hair straighten their hair, right. People who are short wear heels, people who, if their body is not, the muscles aren't big enough, they try to make them bigger. If there's something else about their body, they'll change it. They do all these things, and so the aliens will say, you guys must deeply believe that you are irreconcilably ugly.
Right.
Given how much money is spent on the beauty industrial complex.
They'd be right.
They'd be right.
They'd be right.
They'd be right.
If they were to make those assessments, because they're not even assumptions,
right?
Just assessments.
Yeah, you've got eyelash thickener. What, you don't like your eyelashes? You got powder on your cheeks. What, you don't like the color of your cheeks? You know, you've got paint around your eyelids, and you don't like the color of your what? So yeah, they'll run back home and say there's no sign of intelligent life on Earth. Plus, they all think they're ugly.
Well, you might think I think I'm ugly. Maybe I just think I'm fabulous.
No.
All right.
Chuck, I don't think we have time for anywhere. Throw one more. If I have time, I'll do it. Go.
Okay. Let me find something very quick. I'm gonna.
You don't know how quick my answer is going to be.
Well, I'm gonna make it a quick question.
Okay. Good.
Okay. So here we go. Hello, Neil and Chuck from NAU in Flagstaff. I was wondering if you've heard or know about the idea of black hole stars. I've seen videos taking this hypothetical star that has an insane mass, and it could explain black holes in the middle of galaxies. I asked you this question, I didn't even realize, in a few weeks ago, but any thoughts on that?
Yeah, I don't know what a black hole star would be other than just a star that became a black hole.
Exactly.
Right. I don't know. We have very clear definitions of stars.
What you told me is that we know of nothing that has the mass that would create the black holes that we see at the center of galaxies.
Oh, correct. Yeah, that's an unknown. We don't know what phenomenon is necessary to funnel mass to whatever black hole began there for it to have hundreds of millions of times the mass of the sun. Right. It's still, and James Webb is going to help us figure that out. That's all. It's a frontier.
There you go.
And notice I'm not calling it a crisis. It's just something we don't understand yet.
Exactly.
Right.
That's right.
We don't get all emotional about it. It's just, let's work on it.
All right, so there you go. Pull yourself together, man.
Pull yourself together. You can get through this.
You'll get through this, man. Pull yourself together.
All right, Chuck, that's all we got. That's all we got time for.
That's it.
I love grab bags. Those are fun.
Yeah,
okay.
Always.
Yeah,
so much fun.
Cosmic Queries, grab bag. Chuck, always good to have you there.
Always a pleasure.
Neil deGrasse Tyson here for StarTalk, Cosmic Queries. Keep looking up.